Let's begin. Now, today's session, what we're going to do is we're going to cover, I'm going to give you a bit of time to do 12E along with 12F as well, because they're both the similar type of skills. And then we're almost done for chapter 10, and so we're pretty ready for the SAC coming out. After this is chapter 5, but I'm pretty sure it's not going to be assessed, just because you can't do it all and then get assessed on the SAC immediately. So it's unlikely to be on the SAC. So that means after chapter 10, you've got about 2 weeks to prepare yourselves. Remember, the pillars are chapter 1, chapter 9. You understand functions and calculus, chapter 10 should flow. 2 and 3 should also flow. 2, 3, and 4 are just graphs, transformation, and matrices, right? It's chapter 1, chapter 9 that you've got to get your head around, okay? So we're almost at the end of it. You can see that most of these questions are now applications, and that's all that's left from chapter 10. Yeah, I've got to go back to 10B to make sure you've got your kinematics, velocity, acceleration, and rates of change. But other than that, I promised you that it would be ready for the SAC, and I have gotten you there, yeah? And that's because we spent a lot of time in chapter 1, chapter 9. Chapter 10 was meant to be easy. It's meant to sort of flow. Okay, so today what I'm going to do is I'm going to do some questions from 10F, which really ties in what you've done in 10E, which I'll recap that as well. And then there's only one concept I want to talk about. The difference between maximum value, or absolute maximum, versus maximum rates of increase or decrease. There's a difference between those two. Okay? All right, so let's just recap. What did we do yesterday? What did we do yesterday? What's my name? Luke.
We did a practical use of calculus to solve a problem.
Yep.
It was just to do with a box. And you were getting dimensions, then you had to figure out the equation for it and find out the maximum volume to get out of it.
Fantastic. Now, in that question that Luke was describing, it was a box, it was a sheet of metal, you cut out 4 squares, and you make a volume, and you find the expression was the hardest part. Afterwards, what you had to do was understand what it means to find the maximum volume. And I said that there were 2 skills there. It was 1, when you have a stationary point, that's when you have a maximum or a minimum. Or 2, you had to find or prove whether it is a maximum or minimum, right? What you'll find in chapter 10E is that sometimes the local maximum is not the absolute maximum. So when they ask for the maximum volume, sometimes it's the endpoints as well. Okay, and so that's something that you have to pick up, and that's from 10E. Now, 10E was all about absolute max, absolute minimum, right? 10F, instead of absolute max, absolute minimum, now we're talking about maximum rates of increase and maximum rates of decrease. And I want you to think about what that means, yeah? But let's start off with this question here. You're going to do exactly the same things as we did with that box problem. Your hardest part for this question is to design the expression. The hardest part is to find the expression. Afterwards, everything is easy. Okay, so let's read this problem here. You have a farmer has sufficient fencing. So you've got a fence. You want to do fencing to make a rectangular pen. So you know it's a rectangular shape. And you know the perimeter is 200 meters. Now, this is where the question, that's how it leads you to figuring out what you need to do. It says, what dimensions, so of that rectangle, what are the dimensions that will give you the maximum area? Now, as soon as you see the word maximum, what does that tell you again?
You have to find out the maximum range point.
Fantastic. You either find the local maximum, which is a stationary point, or you find the absolute max. Because we don't know whether the local maximum is the maximum area. It could be the endpoint that is the maximum area. We don't know. The only way to know is if you get the area function. With the area function, you can tell which one is the highest value. So at this point, it could either be the derivative equal to 0 that will give you the absolute maximum, so it's the local max, or it's your absolute max by the endpoint. But you only know that if you get the equation. So, because it says maximum area, what kind of area am I looking for? Area of what? Rectangle, because it says it was a rectangular shape. So if I've got a rectangle, I've got a length and a width. Sorry. Yes. Yes, on this particular answer, yes, it ends up, because a square is a particular rectangle. Because if you remember back in year 8 or year 7, when you learn the properties of a square, properties of a square is that it has to have all sides the same, and it has to have 90 degrees, and there are two pairs of parallel lines, yeah? Well, a rectangle is the same thing. The only difference is you got two pairs of equal sides. But when you say two pairs of equal sides, who's to say this is not, oh, technically it's all the same, but who's to say that's not two pairs? When you say this is equal to that, but then this happens to equal to this, doesn't mean that you don't have two pairs of equal sides. You do. So a square is technically a rectangle. It's a subset. Yeah? So that's why, by definition, this, if I said for a square, it would have to have the fact that they have to all be the same. But when you say a rectangle, you can call this a rectangle. It's just that we gave it a name. Yeah? So, in this particular case here, we've got a rectangle. Area of rectangle we know is length by width. Problem is, we don't know what the length and we don't know what the width is. They haven't told us that, but that's what you have to find out, right? The only other information I've got is perimeter equals 200. Now, how do you find the perimeter of a rectangle? Yeah, L plus W plus W, or 2L plus 2W will give you the perimeter. So in this case here, I can rewrite this expression as 2 times the length plus 2 times the width should give me 200. This gives me an equation. If I simplify it and divide everything by 2, a factor of 2, I get 100 equals to L plus W. Now what you can see, you got two equations here. You got 100 equals to L plus W, and you've got area equals to L times W. Two unknowns, two equations. It is possible to solve. Okay, or possible to reduce it to one variable. Now, what are you going to do with these two equations? Because remember, your goal was to find maximum area. The only way to find maximum area is if you get a function for area. So you want to be able to sketch this graph. And the only way to sketch the graph is you have two variables. In my case here, I've got three variables.
Well, this is 100 minus L.
So if I minus L on both sides, I will now have 100 minus L is equivalent to W. Why did I want to do that? Because if I sub, now I can say W can be replaced as one singular variable, and that will change area is equal to length times 100 minus L. See, that's a nice equation. If you're not used to seeing it A's and L's, then you can replace them with X and Y's. Technically, this means Y equals to X times 100 minus X. And if you expand that bracket there, that's 100X minus X squared. We all know that's a quadratic equation. See, looking at that, that's a quadratic equation. And that means you can sketch that. See, whereas before, without substituting that W, you can't sketch that. You don't know how to sketch because you don't know what L and W could be. You still don't know what L is, but you've now got a function. You got X as the function, or L as the function, and Y as the result. Okay? So now you can say something now. If you know it's a quadratic equation, then to find the maximum area, it has to be the turning point, because that's a negative X squared. You know the graph has to look something like this. So if it's got to go up and down, it's a parabolic shape, then obviously the maximum has to be at the turning point. Now, if we know it's a turning point, how do you find that? What's the point of knowing it's a turning point? How do you find the local maximum again? What do you do? 10C. Jack. Yeah. Why do you differ and let it equal to 0? What's the goal? Why do you have to differentiate this equation and let it equal to 0? Yeah, because we know there's a stationary point up here. The derivative tells you the gradient of the tangent. The gradient of the tangent at the maximum is 0. That's why you say find the derivative, which is the gradient, and the gradient of the tangent, we want that to be 0 because that's where the maximum or the minimum is. In our case, we know it's the maximum. So your goal now is to find out derivative dy dx of this, and that will give you, what's that? What's the derivative of 100x minus x squared? Yes, Kate? Fantastic. What, not x? 2x. Minus 2x. Fantastic. So that tells me that's my derivative, but that doesn't tell me what my maximum is. But we knew the maximum is when the gradient, which is derivative, is equal to 0. So if this is equal to 0, you can now solve for the dimensions of x, or in this case L. Yeah? Now let's solve for that. 0 if you minus 100 on both sides. I'm just going to rub that off, so move this over here. 100 on both sides, you get minus 100 equals to minus 2x. Divide both sides by negative 2. Yeah, 50. What does that mean? It's all about meaning. Okay.
The x value of
Yeah. So that means, back to our problem, x represented your length. When the length is 50 meters, when x is 50 meters, the length is 50, I will get a maximum area. But what was the question? Because I haven't answered the question yet. Most students finish here and they stop. You don't get the mark there. What do you have to say? Yeah. You need to find the dimensions, length and width. So if you know the length is 50, how do you find the width? Yeah, you sub it in, because the width is here. Width is equal to 100 minus whatever L was. L was 50. 100 minus 50 is 50. So that tells me that the length is equal to 50 and W equals to 50 in order to have maximum area. This is the correct answer. That's answering the question there. Saying, so you'd say when length is 50 and width is 50 meters, that's when you have a maximum area. Well, that's the dimensions. Okay, but you don't stop at x equals 50 or you don't stop at L equals 50. It means nothing. Okay, you haven't answered the question there. And that's what you have to do when it comes to your SACs and your exams end of year. That's how you answer it. You don't just write and say that. That's it. Oh, I reckon, well, this is a pretty easy equation. So I reckon 3 is a bit much. I might even reduce it down to 2, but might be likely to have 3. Or what do you include? Yeah. So normally, if they did have this question, which they won't, but if they do, it would be the first step is to get derivative equal to 0. So this line here would be 1 mark. Everything beforehand is now assumed from the previous question. They would have to have it broken in parts. Yeah, they would have a part A say, write the expression for the area, or show that the area equals to this. And then the second part, then they'll say this question or something like that. Or they might say, show that, no, actually they would say that. So they would say the first question, part A, should be show that area equals this. And that means you would have to prove this. So if you prove that step from the first question, and then the second question they'll say, find the maximum area, then you have to do this step. So you get 2 marks from there. So that would make it 3 marks total. So 1 mark for the show, 2 marks for derivative equals 0 and the correct dimensions. So even if you got this right, but you wrote that, you don't get this marking. Okay. So that's, usually, yeah, I'd say about 3 marks if you break it up into those pieces. But usually if they were to do this question, it wouldn't be like that. So it would be something a bit more bizarre, maybe an expanded form, maybe a completed square. But that, the process is the same. So end of year, you should expect something like that. They'll say show, and they'll say, you know, find the maximum or whatever it is. It's likely to be the same sort of style of questioning. Okay. All right, how do we feel about that? It was pretty good? Yeah? So that's what exercise 10E and 10F is. So 10E was to do absolute max minimum. This one is maximum minimum problems. Yeah, that's a maximum minimum problem. And you have to decipher whether it's an absolute max by local maximum or whether you find the endpoints or not. Okay? Now, the only new thing I want to teach today for 10F is, let me just move to that slide. Don't worry about that, it's the same thing. Ah, here we go. Let me just rub this off. There we go. Maximum rate of increase or decrease. I want you to copy this down. Okay, so what is the difference between absolute max, minimum, and now we're talking about maximum rate of increase and decrease?
12 questions like those where you have to find the areas. Would be given like measurement formulas and stuff?
In your exams or even your SACs, you will be given area, like the basic ones like circle, triangle, square, rectangle. Well, actually, I don't think square, rectangle. Triangle, circle, circumference, 3D shapes like sphere, cone, and cylinder. Those are the main ones. That's always on your formula sheets end of year. And it should be on your formula sheet for your SACs as well. Those are the common shapes that they use. Yeah, there's not meant to be any memorization We prefer that you do, but in case you don't, there is a formula sheet for it. All right, here we go. Maximum rate of increase. Now, what you need to understand is when we say maximum rate of increase, rate is how fast something is relative to another. In our case, we're always talking about dy dx as the measurement of your y values as your x changes. So you think about it, how fast does x go across and how fast does y go up? That's the rate of increase, yeah? Whereas how fast x goes across and how fast y drops, that is called the rate of decrease, right? Now, that, in general, we call that the change in y over the change in x, or hence change in y and change in x. So really, it's the derivative. So when you're actually saying rate of increase, you're really just saying the gradient. So when they say find the maximum rate of increase, they're really just saying find the maximum gradient. Now you remember back in chapter 9, I taught you how to sketch reading the derivative graphs. You know, like with a normal function, I said, is the gradient decreasing or increasing, or strictly increasing or strictly decreasing? Remember those points there? That's what you're doing in this case here. So if I gave you a shape, let's say something like that, right? And I ask you, at this particular point, you know, we know one thing is the rate of increase is positive, meaning that the gradient is currently increasing, right? As x increases, y increases, not decreasing, right? But what happens if I chose this point and I move closer and closer and closer to this point? What's happening to the gradient? What's happening? So if I choose a point here, I get this gradient, but then if I choose this point, I get that gradient there. What's happening to the gradients in between? What's happening to the rate? Yeah, it's getting closer and closer to zero, meaning it's getting smaller. So the gradient's getting flatter and flatter, or the rate is decreasing. Okay, so the y values are decreasing. It's not growing as fast. Where's the highest rate? Somewhere over here. Because at that point, at this point here, the tangent is really steep. That means for every little x you move across, it's a high jump for the y. Whereas this, for every little x you move across, it's a very low jump for the y. So we call that a slow rate or a lower rate. Yeah? So it's a slow rate of increase, but we want to find the maximum rate of increase. So in this particular case here, the largest one will be over here, and then the largest decrease will be somewhere over here. Okay, so over here, this is now a rate of decrease. See, the gradient's decreasing, it's negative. It's dropping in rate, but as you move to the right, it's decreasing in further and further. It's getting more steep and steep, or getting steeper and steeper, right? So we call this a rate of decrease, but this rate of decrease is getting larger and larger. So when you say find the maximum, you're really trying to find the maximum gradient. Does that make sense? Okay, now, this is what I want to describe. So let's go back a step on what we did in exercise 10E. Now in 10E, if I gave you this graph, and this is your y, this is your x graph, what do we call that point again? Stationary point. And that will tell you the maximum what? Maximum what? Maximum y value. Okay, it is the maximum that the y values can achieve. But why do we call that the y value or maximum y value? Is because it's your y-axis. True? Okay? And then what you would do is, how do you find that maximum y value? You would say find the derivative, and we know the derivative, which is the gradient 0 at that point. True? That's what we learned from 10C. So at this point, you'd say dy dx equals to 0 at the max y value. Cool? So that all makes sense, yeah? Now, if I then draw, I'll do another one. Same thing. But now the only thing I change is I say the y-axis is my derivative. What would this point represent now? So if I put my point right here. What does that represent? Maximum what? Yeah. Literally now, and that's the only thing that you had to get your head around in 10F, is to understand this represented y value, so this was your maximum y value. This is your derivative axis, so this is your maximum derivative. But maximum derivative just means maximum gradient. Maximum gradient just basically means maximum rate of increase. Okay? Okay, so don't get your head confused between y's and dy dx's. They're both different. Okay, and that's what they're trying to say. Now, if I asked you, well, how do you find the maximum rate of increase? What would you do? Just the same way as you did for the red. What would you have to do? Yeah, literally. That's why the double derivative tells you the maximum gradient, or maximum rate of increase. So if you want to know how to find the maximum rate of increase or decrease, you just simply find the derivative of the derivative. See, this one you said, find the derivative of the curve. Then why would you do the same thing here? This is the derivative of the derivative curve. So that's why we call it the double derivative, because you're deriving it the second time. The double derivative, and you let that equal to 0, so I'm going to write it here in green. The double derivative equal to 0 at the max dy dx value. Just the same thing. So if you look at the two, they're both exactly the same. It's just a definition. So all I'm saying here is that was the y-axis. That is the maximum y. How do I find the max y? You said find the derivative, because you know the gradient at this point is 0. Okay, and you said, all right, find the derivative of this curve. That will tell you the maximum y. Then I'm doing the same thing here. I'm just changing the axes. I'm saying, well, what if that is the derivative axes? You sketch the derivative graph from chapter 9, or exercise 9D. Then to find the maximum derivative, which is the maximum rate of change, you would have to find the derivative of the derivative curve, which we call the double derivative, because you're deriving it twice. Yeah? So double derivative equals 0, that will tell you the maximum rate of change, or the maximum decrease. Does that make sense? Yeah? So that's exactly what it is. So if I were to give you as a sort of formula, or not a formula, but a function so you can see, if I gave you y equals to x cubed, right? What you would have done is you would have said, this is your x cubed graph. That's y, that is x. Okay? If you wanted to find the derivative, dy dx, in this case here, you would say this is 3x squared. And then you sketch 3y dy dx by x, and 3x squared looks like that. True? So if I asked you to find the minimum rate of change, or minimum rate of increase or decrease, right? So in this case, this is my rates. My minimum is down here. That's clearly the smallest point that I could have for my decrease, because this is my rates. This y-axis here represents rates. It doesn't represent y values. This is the y values for x cubed. This is the rates for x cubed. So all the rates are given here. So where's my lowest rate? Right there. That's where my lowest rate is. Again, there's nothing down here. That's my lowest rate. So how do you find your lowest rate? You would say, find the derivative of this when the gradient's 0 at that point. So find the double. So you find the derivative of this curve, and that's what you would say. You'd say, all right, I'm going to find the derivative of this. So that means we say the double derivative, and that would give you now 6x, which I'll draw it over here. Ugh. Double derivative, 6x will look something like this. This is d squared dx squared, and that's your x there. And you'd say, well, at this point, once you find the derivative, you said, let that equal 0, because you know the gradient of the tangent line of this particular curve is equal to 0 at that point. So you let this equal to 0. So double derivative equal to 0, and voila, whoops, x equals to 0, which makes sense, because it's true. If you sketch 3x squared, the minimum has to be at x equals 0. So the double derivative, let it equal to 0, you find the maximum rate of increase or decrease. Okay, but you just have to get your head around that this axis represents rate of increase or represents rate of decrease. Okay, now because it's all in the positive, it's technically increased the whole way, but the minimum rate of increase is down here. Okay, if it's a negative, if it's in the negative region, then we call that rate of decrease. Okay. Does that make sense? Does that tie in what we're doing? Yeah, or watch the video again, or just sit back and really think about that. Yeah, because really 10F, that's the only extra thing I can add on to your understanding. So understanding curve, derivative. This is the derivative, so the second derivative of that will give you the same thing. You can do it on and on. You can even find the derivative of the derivative, or like the third derivative, and that just means find the maximum of the second derivative graph. That's it. And you just keep going and going. Obviously, it works better if I had an x to the power 6. And you can find the maximum of the maximum of the maximum. Okay, but it's more about, and you'll find that you start doing that when you're doing acceleration, velocity, and displacement. So if they ask you for maximum acceleration, you'll find that you have to find the derivative of the acceleration graph. If they want you to find the maximum of the velocity, you have to find the derivative of the velocity graph. And if you want to find, sorry? Yes. And then, yeah, well that's what it is. Displacement, like maximum displacement?
What is displacement?
Displacement in a nutshell is like this. So
Yeah, but
let's
like,
say,
I get it. So like, what about in maths? Like, what is that? What is that equivalent? Like, I mean, what?
I'm confused by what you mean.
It's the highest level.
It's the highest y value. It's the maximum y value.
Yeah.
So,
I'm not sure what you're trying to say.
Displacement's y.
All right, I'm going to leave you guys there. That's exercise 10E, 10F, yeah? So practice that. That's what this session's about, and you got your weekend to practice there. I'm going to pause the video, and then I'll come around and help.